Okay, friends, welcome back. Good morning to you. So today we're picking up where we left off last time. I had showed you this one last carbocation rearrangement where it's not a methyl group or a hydride that shifts over, but it's actually one of the atoms, one of the other, this is called an alkyl shift. And it contracts the ring from 5-membered ring to from a 6-membered ring to a 5-membered ring. The reason this happens is because it allows a more stable a less stable secondary carbocation to rearrange to a more stable tertiary carbocation. You don't need to worry about ring strain here. It's not about ring strain. 5 and 6-membered rings are only have slightly different, marginally different ring strain. Both of them are okay. So there's not a huge change in stability when you go from a 6-membered ring to a 5-membered ring. The biggest thing that's happening here is that a secondary carbocation is becoming a tertiary carbocation. And then for those of you that are struggling with this a little bit, let me just recommend one quick thing. If you copy all of that down and then you replace carbons 5 and 4, and you just write an R group in the place of carbon 6 and an R group in the place of carbon 3, and then you do the 1-2 rearrangement, then it's not so very difficult to see how alkyl group can shift over. It's just that these two happen to be attached to each other, and that's where the ring comes from. So if you have a hard time visualizing that, abbreviating things might be the right thing to do. Now, once you get to that rearranged carbocation, you need to consider, in this case, since the conditions were alcohol dehydration conditions, you need to consider the elimination products that could come from either of, from any of the protons that are beta to the, let's see what colors I've used so far. Any of the protons that are beta to the positive charge. So if we remove the pink proton, we get this product. If we remove the gray proton, we get this product. And I would expect you to draw all of these that have check marks by them as products of this reaction, rearranged and not rearranged. And I'm not going to expect you to tell me whether the rearranged products are present more than the non-rearranged products. I'm not going to expect you to tell me whether products from this alkyl shift are more present than products from this methyl shift. If you had to choose which alkenes you thought would be major, you would choose the ones that are most substituted. I've got 2 tetrasubstituted alkenes. So I suppose if you had to pick a winner, that would be a decent one. But in any case, you would draw all of these as products. Okay? Yes?
Can you add a hydride on the cyclopentane as well and maybe the positive charge to the other tertiary group?
Try one more time because I'm missing the premise. What about the cyclopentane ring?
Well, could you move the pink hydrogen to...
Okay, right. So the question is, could the pink hydride move over and put the positive charge here? That would be a rearrangement of a tertiary carbocation to another tertiary carbocation. Such things are known in chemistry. They actually happen a lot. But I'm not going to have you predict them because you're not going downhill in energy. Later, when you learn about the biosynthesis of cholesterol, you will see that there are a ton of carbocation rearrangements in that process, and some of them involve tertiary to tertiary. But remember, the situation you're looking for is, where you're going to worry about it, is a secondary carbocation adjacent to either a tertiary or a quaternary carbon. So no, you wouldn't worry about that as far as I'm concerned. Yep. Okay. Well, you've seen that going through carbocations can give you a mess of products. And so what we're going to do for about half of our time, a little bit more than half of our time today, is we're going to talk about how to avoid carbocation rearrangement with alcohols. The theme is still going to be turning the OH into a good leaving group, but the techniques I will show you convert OH into a leaving group that's not really going to leave on its own. There's not going to be a good explanation for that, by the way. So some of the things we're going to do today, you're just going to have to memorize. But importantly, these techniques will avoid carbocationic intermediates, and so you can do chemistry with alcohols under a little bit more of a controlled way. I will say at the beginning of this that mechanisms for these reactions are known, and in many cases, the mechanisms are shown in your text. Nevertheless, they don't help a lot. And the reason they don't help a lot is that they're using unfamiliar reagents, and if we spend too much time on the mechanism, I've found that students get caught up in questions that I don't have answers for. For example, why doesn't that just leave? I don't know. And so what we're going to do is I'm going to show you these reactions, these reagents. If you want to talk mechanism a little bit, we can, but I want you to focus on the outcome of the reaction as a result of avoiding a carbocationic intermediate. Whenever you're in a situation where you have to memorize reagents because either there isn't a great explanation about how they work, or there is, but it's just not worth our time, let me recommend 3 sort of strategies for you. You can do this for every new reaction we talk about. If you like flashcards, you can write a card that has a starting material, and R is going to be for reagent, and then you have to identify the product. That tests whether you really understand how the reagent works, and in particular, if there's stereochemical issues there, you can choose an example that'll test your knowledge on that. Also useful is to be able to take a starting material and a product that's known and then have you guess what the reagent was. That's a way to help you start thinking backwards, which is a really important skill for doing synthesis in organic chemistry. And then another sort of backwards thinking reaction is where, backwards thinking flashcard is where you have a product and a reagent, and then you have to think backwards to the starting material. I'll illustrate this process with a few of the reactions that we talk about. So, avoiding the carbocationic intermediate, we're going to do sort of SN2 type reactions first, SN2 reactions of alcohols, and then we'll do a dehydration reaction of alcohols. Okay, so strategy number 1 is to use PBr3 to convert the alcohol into an alkyl bromide. So PBr3 is an unfamiliar reagent. It's a bromination reagent, and it converts the OH into a leaving group, which I'm just going to illustrate like this. Remember, the whole story in this chapter is that OH minus is a terrible leaving group. I'm not really showing you what that is. I can draw it for you, and we won't worry about the mechanism. As I said, the leaving group ends up being a phosphorus bonded still to 2 bromines, and then and also to an oxygen. So this ends up being the leaving group. Now, somebody out there wants to know, how is that different than just the OH2 plus leaving group that we've dealt with so far, and why doesn't that leave on its own? I don't know. I got nothing, sorry. But empirically, we know that it doesn't because you only observe this stereoisomer. This is a case where the chemical outcome of the reaction tells you what the mechanism must have been. You don't get the other stereoisomer. You see inversion of configuration. That's consistent with backside attack, which is a hallmark of an SN2 mechanism. So even though we don't understand why this leaving group doesn't leave on its own, the results tell us that Br minus must have attacked this leaving group from the backside to give us this product. Okay? So you don't need, the mechanism for this reaction is shown in the text. You do need to know that it proceeds with backside attack and inversion of configuration because it's an SN2 reaction. You don't need to know how to get from the alcohol to this leaving group, and you don't even need to know what the structure of that leaving group is. So long as you know that PBr3 turns OH into a good leaving group, but then that Br minus attacks from the backside and you get SN2 chemistry. This reagent works, we're going to use this because the mechanism is SN2, we're going to use for primary and secondary alcohols, but not for tertiary alcohols because, of course, sterics prevent the SN2 pathway for tertiary alcohols. If we want to do stuff with tertiary alcohols, we'll just use HBr. Okay? Yes? If you use PBr3 in the presence of another good nucleophile, could you get another product? In general, what people will do, the answer is, in general, what people will do with PBr3 is they will take their alcohol starting material, they'll do the PBr3 reaction first to get this, and then they'll do a subsequent SN2 reaction. We could imagine, for example, using sodium azide, which is just N3 minus and Na plus. You could imagine then doing any type of chemistry that we've done before on alkyl halides once you've got that intermediate. So yes, in a second step, if people don't usually add the nucleophile in the same step as PBr3, they'll do it in a second step. So what I've shown you here is a two-step synthesis where we are using PBr3 to convert the alcohol into an alkyl halide, and then we're doing something else with the alkyl halide. So just to illustrate the three ways of thinking about a reaction, if I were to give you something like this and then show PBr3, you would need to be able to draw the product. And the right product, maybe on the back of your flashcard, would be something like, well, fine, we'll make that. Something like this. You need to show inversion of configuration. Then an alternative way to test your understanding would be to show this and the starting material. And then you have to know, okay, the choice here is going to be between PBr3 and HBr. If you choose HBr, you won't get the pure enantiomer, so you need to use PBr3 to get inversion of configuration. And then finally, another interesting way of testing yourself is going to be to give you the product and the reagent, but then you think backwards to what the starting material must have been. So if you need help remembering reagents, doing flashcards like that is an effective way to keep in your mind what each of those reagents does. Yes?
Where can we find all the details to put on a flashcard? Like I get like this reaction we can put on it, but are there other reactions in the textbook that we can put on a flashcard?
So you will see at the end of each chapter is a summary of the reactions we've talked about there, and that's a good place to go to see everything. Yeah, at the end of the chapter in the textbook. Also, the study guide will tell you very clearly what reactions to pay attention to. Yeah. Yeah, so we're reaching a point in time where So far, we've sort of just been able to figure everything out based on first principles, and that's going to continue to be a thing, but there are going to be some reagents you have to remember. Some details about those reagents you have to memorize. And therefore, if do whatever works for you to memorize things. We don't want to rely exclusively on memorization, and that's why if you can connect the idea of PBR3 to SN2, then you're probably most of the way there, even if you haven't memorized all of the details. Okay, so that's strategy 1. Strategy 2 is very related to it. In fact, it almost shouldn't be a second strategy, but this will be using SOCl2 and a base, pyridine, to convert an alcohol to an alkyl chloride. Again, the mechanism is going to be SN2. I wonder what's going on there. That's weird. I didn't even say seriously, which sometimes causes Siri to start up. Anyway, start with this. I'm choosing an alcohol with the stereocenter just to illustrate it. SOCl2 and pyridine. Pyridine is a base. You can draw it. It's a 6-membered ring that looks like this. Why you need a base for this reaction is not clear because you didn't need one for PBR3. And so often students want to know what's the deal with the base there? What is it doing differently than was done in PBR3? The answer is I don't know. Often when you are discovering a new reaction, you'll get it to work to some extent, and then you will do what's called optimization, where you tweak the reaction conditions to make the yield better. Sometimes you'll add things to the reaction to make the yield better. In the same way that if you're cooking, you'd be like, let's add a little bit more salt to that. And sometimes there won't be a clear explanation for why what you've added makes the reaction go better, and you don't care because it made the reaction go better, so yay. So this is a case where I don't know why pyridine is included. If you forget it and just do SOCl2, that's probably fine. But the point is that SOCl2 will convert the OH to a good leaving group, and then in a key step, Cl- will come along and attack from the backside to give you the alkyl halide product. And again, you see inversion of configuration, which is consistent with backside attack, which is what we expect for the SN2 mechanism. So again, you don't need to know the structure of this leaving group. If you want to know it, it's in your text. The mechanism is shown there. You can go look at it. It may or may not be helpful to you if you want to know that, but I'm not going to ask you questions about it, about what the leaving group is. Instead, however, I do want you to know that once OH gets converted to a good leaving group, the mechanism is SN2, and so you get inversion of configuration. All right? So because this is SN2, we'll do this for primary and secondary alcohols, but not for tertiary alcohols. If we want to make an alkyl halide out of a tertiary alcohol, we'll just use HCl. You can do follow-up reactions after the fact with the resulting alkyl halide. For example, if you chose in the first step to use SOCl2 and pyridine. By the way, there's often no meaning associated with something being above or below the arrow, so don't worry about that. It's mostly a question of whether I ran out of space or not. SOCl2 and pyridine will replace the OH with Cl, and then you get a backside, will replace the OH with Cl in an SN2 reaction with backside attack. And then again, you're free to do whatever reaction you want. If you use a good nucleophile that's not a good base, you can do a nice SN2 reaction where the nucleophile appears here. Okay. Questions about that? Okay, so here is an interesting conundrum. I want you to go back here to this two-step synthesis that we did with PBr3, and we did another example of a two-step synthesis with SOCl2. Suppose that I wanted to start with this alcohol, and suppose for whatever reason I wanted to get only that. I wanted to get that azide product, and I wanted it to have wedge stereochemistry instead of dash stereochemistry. I got a problem if I'm going to do PBr3 or SOCl2 because both of those methods convert OH into an alkyl halide, but they use inversion of configuration. And so by the time I go here, you see I can't do an SN2 directly to get to that because I get the wrong stereochemistry. Am I explaining that okay? Yeah? Okay. So what's the strategy? How can I get the desired stereochemistry when it's, when if I do it the way that we've learned above, I should get the other stereochemistry. So here, our goal needs to be to convert OH into a good leaving group without having a subsequent backside attack like we had for PBr3 or SOCl2. So it turns out there is a reagent for that. Now, why it works, again, is not going to be 100% clear. I'm going to show you the good leaving group, and I'm going to tell you it's stable, and it actually doesn't get attacked by the chloride, and you're going to be like, why not? And I'm going to be, I don't know. So again, what I'm about to show you is a detail that is useful, but that you'll probably have to memorize in terms of the reagent. So use a reagent called TSCl, that's toluene sulfonyl chloride. To convert an ROH into a type of product which we will call a tosylate, which is a stable good leaving group. And this process does not involve inversion of configuration, in part because it doesn't involve the carbon at all. So I'll show you what TSCl looks like. Again, the reagents for doing this are TSCl and pyridine. Why do you need pyridine? It's a base. I don't know. I think it's probably to remove the proton that's on the alcohol after it attacks the TSCl reagent. The mechanism for this reaction is known, and it's in your text. I won't ask you to know the mechanism other than the details that we will talk about. So toluene sulfonyl chloride looks like this. You're going to get it confused with TSOH. So I'm just going to make a note here not to be confused with TSOH. They are structurally related, but there is one key difference. In TSCl, or toluene sulfonyl chloride, there's a sulfur bonded twice to oxygens, doubly bonded twice to oxygens, but in the TSCl reagent, this group here is a chloride, which is a leaving group. What ends up happening, and again, what I'm going to show you some mechanistic steps so you can follow along a little bit. We're not going to draw a full mechanism for this, mostly because it's in your text and it's not really worth our time. It's not going to help that much. OH will attack the sulfur and the chloro will leave. That's going to get you to an intermediate that looks like this, where there's a positively charged oxygen, and then the oxygen is also attached to the sulfur. And then your base, pyridine, probably removes that proton on the positively charged oxygen. And that's going to get you to the product for this reaction, which looks like, oh, somebody was going to stop me from doing that, right? Somebody was going to tell me, why is there a change in stereochemistry there? There isn't. That carbon that the oxygen's involved with is not participating in the reaction. It's only the oxygen that attacks the sulfur. So stereochemistry at the carbon remains unchanged. And this is the product. Now, we get tired of drawing things like that, so we're going to abbreviate all of, we're going to abbreviate all of this with the letters TS. So this equals O and then TS, where TS represents the gray stuff, okay? Now, this is stable. It's a good leaving group, and you can use it in subsequent reactions. You can use it exactly in the same way as an alkyl halide. So in other words, it can do SN2 and E2 reactions. But importantly, it's stable. You can put it on the shelf and nothing's going to happen to it. Meaning we have just converted OH, I'm going to now highlight it in green, into a good leaving group. Looks like an avocado now. Into a good leaving group without any backside attack. Now, why does this work and why didn't that happen before with SOCl2 and PBr3? Presumably, the tosylate leaving group is not a good enough leaving group for a nucleophile at this stage to come in and displace it from the backside. Some of you were wondering, well, Cl- is hanging around after it left from TSCl in the beginning. Why doesn't it do backside attack, and why don't we see SN2 at that stage? I don't know. I got nothing. But the fact is that you can isolate this. So now you've got some stereochemical versatility. Now you can take the OH, the alcohol that we talked about, you can use TSCl and pyridine to convert the OH into the tosylate leaving group without any backside attack or inversion of configuration. And then if you want to, then sure, you can use N3- or another nucleophile to do an SN2 reaction, and then you can get the desired stereochemistry. All right, so it's really fun to write questions on exams where I show you a couple of different options. I'm just making stuff up at this stage, but we'll go, I'll put a big question mark here, and then I'll put like CN there. And I ask you, how do I get from there to there? And then it's also fun to do a question like this, where I take the same starting material, but then say, what if I want the other stereoisomer? Okay. This is where thinking forwards and backwards through the reactions can be useful. Up above, if I notice that OH is been replaced by CN-, but the stereochemical chemistry hasn't changed, I know that OH is not a good leaving group. So the fact that it's still a wedge there suggests I had to do 2 tandem SN2 reactions. I'm going to switch stereochemistry once, and then I'm going to do it again. So one strategy would be to use PBr3. That's going to make this alkyl halide, and then in a second step, use CN minus. Okay, we're not going through that very slowly, but do you follow the rationale here? Switch to the bromide with inversion of configuration, then add another nucleophile, and then do inversion of configuration again. You could call this the double inversion strategy. And it looks like double inversion looks like retention of configuration, right? The nucleophile, the thing that we replaced, the thing that we replaced OH with, this nucleophile, ends up having the same wedge type stereochemistry. If we wanted to do what's below, where the nucleophile is that we replace the nucleophile that replaces the OH group is now a dash rather than a wedge, that's going to involve only a single inversion strategy. That's where we're going to want to use toluene sulfonyl chloride or tosyl chloride or TSCl to first convert the OH into the tosylate leaving group without changing stereochemical configuration, and then in the second step we would add CN minus. Okay, so questions about that? Yeah, go ahead.
I just want to double check I'm getting this. So for the double inversion, if we use SOCl2 and pyridine, that's the same.
That's right, yeah. If you wanted to use SOCl2 and pyridine, do the same thing that PBr3 does, only with chloride. Yep. Yes?
For the TSCl and pyridine reaction, would that still be considered SN2 because the leaving group is leaving at the same time that it's attacking, or is it like something different?
So the TSCl and pyridine reaction, are you talking about this step?
Yeah, like the overall reaction as a whole, so you're all talking about like SN2, it's kind of grouped under those, but...
Yeah, so how would you describe this reaction? When we've used the term SN2 before, it's always been for a carbon that has a leaving group and a nucleophile attacking the carbon. I think the question here is, there's two arrows in this reaction. The nucleophile is an alcohol. It attacks the sulfur and the leaving group leaves. Is that mechanism SN2? You can think about it that way, but I'm worried that if you do, you're gonna get confused and say, oh, SN2 always has inversion of configuration, therefore I need to switch the stereochemistry at the carbon. Which of course you're seeing the carbon isn't the thing that's attacked, and therefore there's no switching stereochemistry there. So I would be a little bit careful about calling this SN2 just to avoid that confusion. Yep. Yes?
So going back to what you just wrote down, so let's say like you do your first step, you do PBr3, and then you get that middle step, and then the second step is to add CN minus. Would you then do like, is this a strong nucleophile, a strong base?
Yes, so at the stage that you have the alkyl halide, that alkyl halide is capable of SN2E2 and SN1E1. So you'd want to be careful and just do everything that you learned from, right? Man, I got to remember all that stuff from chapter 7 and 8.
Got it. So like on the test, then you could do that, and like what are like the possible
That's right. What are the possible products? Now again, in a synthesis sense, you're going to try to avoid problems like that. Yeah. But I think what you're asking is, let's just make this problem only a little bit more painful by saying, what if instead of CN minus, which is a good nucleophile but not a good base, what if instead you chose to use ETO minus, and this could be written in any sort of the following ways. So yes, you would expect to see this product, but then you would also expect to see the elimination products that could come from this alkyl halide, which I believe would be these two. Yeah. Okay. So there's one more that you need to learn. People like to, I found that students like to pronounce reagents. So instead of saying SOCl2, people will say SOCL, which is fine. SOCL. TSCL doesn't work quite so well, so I just call that TSCl or tosyl chloride. I told you that we would have an elimination reaction that could do dehydration reactions of alcohols, elimination reactions of alcohols without a carbocationic intermediate. So that, and we're just going to learn one, is a reagent called POCl3. So there's lots of, in this chapter, there's lots of phosphoruses and lots of chlorides and some oxygen. So people will call this POCl, but not to be confused with SOCL. And pyridine happens to be a base in a lot of these reactions. Again, not completely clear what is going on. So let me draw an example where you've seen carbocationic rearrangement before, right? Had we used H2SO4 or TSOH to do the dehydration reaction for this molecule, you would have expected to go through a carbocationic intermediate like this that would have undergone a 1,2 methyl shift to give a more substituted, more stable carbocation that looks like this. And then you would have had to draw elimination products that come from all of those possible intermediates, including this one and this one. Okay? You would have seen rearranged products and not rearranged products if you had gone through a carbocationic intermediate. In contrast, with our good friend POCl, you only see the non-rearranged product exclusively. And the reason for that must be that there is no carbocationic intermediate, and so the mechanism is basically E2. Now, again, if you want to see, the strategy here is essentially the same as we saw before. POCl turns OH into a good leaving group. And if you want to see that mechanism, it is in your text. You're welcome to look at it. It doesn't help that much, but I often felt when I was a student that if I didn't see the mechanism, I didn't really understand what was going on. So I encourage you to look at it at least. I'm not going to hold you responsible for knowing the structure of the good leaving group or how the OH gets turned into the good leaving group, but you do need to know that the reaction is E2, so all of the regular E2 issues apply. That is, the proton that gets removed, the beta proton that gets removed must be anti to the leaving group. And then your base, pyridine, is going to remove the beta proton, and there's only one kind of beta proton here. Electrons kick down and leaving group leaves, and that's your elimination product. Okay? So, now you could, knowing that this elimination product happened, you could go back to the SOCL reaction and even to the TSCl reaction and say, how come we didn't see elimination there? We had pyridine, a base there, we had a good leaving group, what's going on? And the answer is, I don't know, and I'm sorry. So that's a detail that you need to memorize, but it's synthetically useful because this allows you to make alkenes out of alcohols without having to worry about carbocation rearrangement. Okay, questions? That's 4 new reactions for today, but we're gonna make it 5. Right? Okay, so what we're gonna do next fits into the theme of OH minus and OR minus are generally bad leaving groups, with the exception proves the rule. Epoxides are an example of an unusually reactive ether. And an example when OR minus as a leaving group is okay. And the reason you're going to see that it's okay is because of ring strain. Okay, so let's talk about what an epoxide is. An epoxide is an ether where the oxygen is attached to 2 carbons, A and B, but those 2 carbons, A and B, are actually attached to each other. So an epoxide is a 3-membered ring containing ether. You can draw epoxides in a couple of ways. Here's a very simple epoxide called ethylene oxide. We won't worry about how to name epoxides. There is a strategy for that, but we don't generally care. This one's called ethylene oxide because it's like you took ethylene, a carbon-carbon double bond, and then just stuck oxygen on it. We will learn how to make epoxides. There will be 2 strategies for making epoxides, but we won't quite do that yet. There are actually 2 questions on your problem set 8 that involve making epoxides one question on your problem set 8 that involves making an epoxide via an SN2 reaction. It's not too hard, I encourage you to look at it, but before we even worry about that, we're gonna just deal with how the reactivity of epoxides, okay? So what you need to know, there's 2 different ways you could draw an epoxide. One is like this, and the other is to draw the ring oxygen as a wedge on either side. There'll be dashed hydrogens here and then hydrogens in the plane of the page here. It's fine to draw it either of these ways. Sometimes it'll be more convenient to use one versus the other. Okay, so the key feature of an epoxide is ring strain. Of course, those are sp3 hybridized carbons, and yet you have constrained the required bond angle in a triangle like that. Ideal bond angle would be around 60 degrees, but the ideal sp3 bond angle is 109. So we're about as far away from that as you can get. Some of you are like, it's 109.5. I'm like, good for you, but I don't care. So the ring strain makes it so that the epoxide is spring-loaded and ready to pop open. And what that means for the epoxide is that RO minus, what am I talking about there? I'm saying the oxygen attached to either of these 2 carbons, I'm calling OR minus, is an okay leaving group for an epoxide because of the ring strain issue. So it's totally fine to take an epoxide like this and then have a nucleophile, and it needs to be a good nucleophile like OH minus. So yeah, let me show you. We would use OH minus, and this would be in an aqueous solution. OH minus could attack, And the mechanism of epoxide opening is SN2, meaning we're going to have backside attack. And if there are stereochemical issues, here in this particular example there are not, but if there are, we're going to see backside attack with inversion of configuration. Showing you this, OH minus attacks one of the two carbons of the epoxide. In this example, the two carbons in the epoxide are identical. We will deal with how to do the reaction when they are not identical. OH minus attacks one of the two carbons and the leaving group leaves. At this point, you're like, hold up, I thought you said that negatively charged oxygens were terrible leaving groups. I did, and that is true, but the relief of ring strain when the leaving group leaves, in this case, this is the leaving group, the relief of ring strain when the leaving group leaves pays for the leaving of the poor leaving group. So your intermediate looks like this. I'm showing inversion of configuration, even though this isn't a stereocenter at carbon A, by having the OH be on the opposite side of the molecule from where the leaving group was, and by having these hydrogens, which were angled towards the bottom of the page, now angled towards the top of the page. Now, because we're in water solvent, usually the negatively charged oxygen of the epoxide is going to pick up a proton from solvent, or we'll add water during the workup stage when we're preparing the reaction for purification. And the final product that we get is going to be this molecule, and the structural feature, the structural pattern of this molecule is, we'll call this carbon 1 and this carbon 2. On carbon 2, you have the OH that was your leaving group, and on carbon 1, you have whatever your nucleophile was. And so anytime you see a 1-2 pattern of nucleophile and OH, you need to be thinking, I could have gotten that by epoxide opening. Okay, are there questions about epoxide opening? Let's do one or two simple examples. There are more issues to get to, more things that we'll need to do a little bit next time. But let's figure out how to deal with stereochemistry first. All right, so suppose we have an epoxide that looks like this, where there are now methyl groups. I've deliberately chosen this example so that carbons 1 and 2 are identical. So it doesn't matter which of the two carbons gets attacked, okay? Let's use MEO minus as our nucleophile and MEOH as our solvent. MEO minus is a good nucleophile. Oh, and generally I will say with epoxides we only worry about SN2. We don't worry about elimination reactions. So some of you have learned to think of MEO minus as a good nucleophile that's also a good base. That is true, but we won't be worried about a competing elimination reaction here. So nucleophile attacks one of the two identical carbons and the leaving group leaves. We need to show inversion of configuration. We'll leave carbon 2 exactly the same as it was. We'll put the bond between the methoxy group and carbon 1, now pointing downward to the bottom of the page. The methyl group is still going to be a wedge, but now angled towards the top of the page. And the hydrogen is still going to be a dash, but now angled towards the top of the page. Okay, so that's all we have time for today. We will continue epoxides on Friday before we move on to chapter 10.